Hi, good morning, and welcome to the ZP Developer Zone. So every Thursday at 8 a.m. London time, we like to do this webinar for the members of our ZP Developer Zone. We like to answer technical questions around electrochemistry, electrochemical biosensors, and biosensors in general. So first thing I'll do is just jump in and say there's obviously a great resource online. So people who are wondering about electrochemistry and electrochemical biosensing in general, take a quick look at the ZP Academy. We do these webinars every Thursday at 8 a.m. London time. And the reason I bring that up is because, if you've got questions, you can find that if the questions are a little bit more deep, then we'll bring them to this webinar and we'll answer them there. We do have collaborations, we do post jobs, we do have the developer zone, and we do workshops. We've got about 5 questions a day, which kind of obviously averages out about 6 minutes per question, but some of the questions are quite deep, so I will go a bit faster. Just to say that we do have a whole series of workshops at the moment. And by the way, underneath this video, I've already posted a lot of links. So if you kind of see something that's interesting, like this Horton workshop that we're doing the 30th of November and the 1st of December, that'll be a workshop around CGM, continuous glucose monitoring. We're also doing a CGM workshop, continuous glucose monitoring, on the 10th of November in San Diego, California. And we're also doing a CGM workshop in Grenoble, in France, on the 4th, and I think it's on the 13th and 14th of November. But I've put the links underneath the video if you're watching it on YouTube. So we do this every Thursday, 8 a.m. London time. Workshops is something that we also do sort of to supplement the learning on this. And I will go forward a little bit now. So these are the workshop links, but they're also underneath the video, so no need to sort of take a note of those. And I will go forward. We're also doing a workshop in India. The workshop in India is, you can find the link here. And again, I will put that link underneath the video. So there's, at this point, I think it's fair to say that I've just mentioned workshops in Norway, San Diego, California, Grenoble, France, and we're also doing in 2 cities in India as well. So there's plenty of opportunities to kind of learn about electrochemical biosensors firsthand. We do have the ZB Academy, and there are a couple of free courses on that. Again, that link is underneath the video as well, so no need to make a note of it. Now really to the heart of this. So these are the questions that we've had this week. So we had a question that come in, and it was kind of one of these questions that you realize, the person asking the question is definitely sort of an industrial engineer. So we do like those questions, and it was about the detection of ammonia and hydrogen peroxide. So we will touch on that. We will also talk about techniques to use with which sensors. So for example, if you're using an electrolyte sensor, sort of potassium, sodium, then you would be using potentiometric methods mostly, because they're ion selective electrodes. If you're using glucose lactate, they tend to be enzymatic, and we tend then to use amperometric techniques. If you're doing immunoassays, trying to detect proteins, maybe molecular assays like RNA, DNA, then we tend to use impedance spectroscopy. So yes, there are lots of techniques out there, and the technique that you use really depends on what you're trying to detect and the kind of assay type that's below that. So we will discuss that. We've also got a question here about measuring glucose lactate and nitric oxide in cell culture media. I think the nitric oxide one's quite interesting because not everyone is aware of nitric oxide, but it is a sort of important signaling molecule in biology. Then we did have a question around alcohol sensors. It was really about, what's our mechanism of detection in alcohol sensors, whether it was just a plain platinum electrode or whether there was some specification inherent in our sensor. And because we're using an enzyme, the answer is it has a sort of an inherent, I want to say specificity. I'm very careful with the word specificity and selectivity. It's a very it's good specificity because we are using an enzyme. And then finally, it sort of it ties together a lot of what we discussed. That we people are asking, what electronics can I use when I'm building a product in order to drive these different types of sensors? So we do have switchable single-purpose sensor circuits. So what I mean by that is, I'm just going to sort of wrap it up, not wrap it up, but sort of. So let's say you made a glucose sensor. You will have an R&D phase where you're kind of using R&D instruments. But from Zimmer and Peacock, then you can actually purchase a final board that's flashed in such a way that actually it will run the glucose sensor. Same with an alcohol sensor. You will have an R&D phase maybe, but actually there is a point where you will actually need a circuit to run that alcohol sensor. And again, ZP has these little circuits for doing that. So now I will sort of drive on a little bit faster and say that we did have a question around about measuring ammonia and hydrogen peroxide. They didn't really say the gas phase, vapor phase, but there's a whole discussion about, if you're measuring ammonia, are you measuring it in the gas phase or the vapor phase? And it's definitely the same with hydrogen peroxide, that people talk about hydrogen peroxide sensing. Well, they sometimes talk about gas phase sensing, but strictly speaking, hydrogen peroxide's actually in the. I just want to say good morning to Aftab this morning. Lovely to see you, Aftab. So the first question is around ammonia and hydrogen peroxide, and I'll jump straight into it. Sometimes people don't often realize that actually they think things are in the gas phase when really they're in the vapor phase. I know it sounds a little nuanced, but it's a true statement, let's say. So they're designing a prototype decontamination system. So many people these days are actually, I think they call it fogging, when they're using a vapor of hydrogen peroxide to clean a room or clean surfaces. The hydrogen peroxide essentially settles on the surface, and it's quite a biocide, is hydrogen peroxide. I haven't heard so much about ammonia being used in that, but I could see that ammonia would also potentially be the same kind of, let's say, biocide. They have a certain temperature range, they have a certain humidity, they have the concentrations that they have, by the way, are it's hard. The concentrations, I think, I want to say fairly nominal in some ways, that, but 700 ppm or 70 ppm, these are quite high concentrations in our world, and so makes them easier to detect. I can't remember the threshold, but there is some sort of threshold with hydrogen peroxide below which the room is considered sort of safe, and above which the room is considered non-safe. So you can see that why you need a sensor in that situation. Now, they ask here, do we have a sensor that gives out a signal of 4 to 20 milliamps, or a sensor that has CAN capability? So these are sort of industrial standards. At ZP, we are aligned with industrial standards, but I'll sort of discuss it a little bit more. I have already contacted this person and sort of say I'm not entirely certain that we have what they need, but I will at the same time make a sort of, I wouldn't call this formal, but a more detailed response. So we have hydrogen peroxide, and here we have ammonium, and I understand they're asking for ammonia. So it's a small. Spelling wise, it's a small change, but it's a little bit, it's quite significant. So we're part of Industry 4.0 and at Zimmer and Peacock, and at Industry 4.0 we also mean Lab 4.0. These are definitely concepts now that many vendors are adhering to, and so though I've been working with 4 to 20 milliamp type signals and CAN protocols for personally, I've seen it back 20 years ago. What we're actually doing is OPC-UA, Open Platform Communication, United Architecture. So I'll describe what we're doing. So for example, we'll have a sensor. The sensor will communicate to one of our base stations, and the base station, and we do have these mesh network starter kits, by the way. And the data will go to the cloud, and there it can go from the cloud. You can send it to an app. You can have several sensors, all essentially communicating with one another, so we can get some distance going on that. But then we can send the data, or the data can go to our cloud and can be called upon using an application program interface, an API, and we make sure that those are OPC-UA compatible. So the questioner is asking whether we will give them signal directly, let's say from a circuit board via 4 to 20 milliamps. Now what we do is we actually send the data to the cloud, and then you can call upon it into your cloud system. So I suppose at Zimmer and Peacock, there is a whole, part of the industry that does, 4 to 20 milliamp signals and CAN protocols and RS-232. But what we do is we bring the data to the cloud, where we can process it, and then people can have an API that calls upon our cloud. So we do have the hydroperoxide sensor and an ammonium sensor. It's not the same, obviously, as an ammonia sensor, but we don't do 4 to 20 milliamps. We do. We send data to cloud, and then on cloud you can call it across using an OPC, Open Platform Communication United Architecture type protocol. So we do adhere to industry protocols. It's just unusual now. And, well, I think the world has changed, to be honest with you, that things have become the Internet of Things. So we are trying to kind of condition that signal so that it's actually useful to people, rather than just giving an analog signal out. It's essentially giving a digital piece of information out. All right, I'll go a bit quicker now. So question number 2 is which techniques use with which sensors? So I did just say that we actually do these whole series of workshops, and it's probably worth saying in those workshops, the slide, this is one of the slides that I actually use in, or the slide I'm about to show is one of the ones I use in the workshop. And the question here is, do I use EIS, cyclic voltammetry, amperometry? What do I know when to use, and what do I use and when do I use it? There are free courses, the ZP Academy. This is linked underneath the video, so there is the ZP Academy. There is actually another, we're a bit eclectic at Zimmer and Peacock. There is also a bunch of other videos. There's probably over 10 hours worth of videos, unfortunately, in this, but in what we call the educational video zone. Again, I have linked to that. And we also have a application zone. The application zone is quite useful because in the application zone, you'll see live demonstrations of at least oxygen, glucose, lactate, and then you'll start seeing the ion selective electrodes, like maybe pH is there and potassium is there and probably sodium is there. So by watching those videos, you can actually see how we program the R&D software. So there are videos on what techniques to use, and I think maybe the easiest one to engage with is the application zone videos, and that is linked underneath this video. We do have the education zone. Those are kind of generally longer videos, more theoretical videos. And we also have the ZP Academy also as well. So there's kind of 3 zones. Everything I've just mentioned, they are linked underneath the video. I just did it this morning. Though this, I have mentioned that we've got a webinar with, not webinar, sorry, we've got a workshop with Technando in India, and we'll see you have workshops in France and Norway and US. Those are all booked. And one of the slides I use in that we obviously do these workshops, they're well attended, and they're actually very quite practical. So we make a point of people making, and in this one, people were making lactate sensors, oxygen sensors, and glucose sensors. They made their own sensors and they tested their own sensors. So it was like, there was a real sort of smile on people's faces that you make something and then you test it and then, it works. So, I think it was well received. But one of the slides we use is this one, and this one describes amperometry. So we will describe electrochemical techniques and we'll introduce amperometry. And the classic sensor in amperometry would be the glucose sensor. So we describe the glucose sensor. People make a glucose sensor. We then describe the oxygen sensor, which is quite nice because the oxygen sensor sort of runs in exactly the same technique, but it happens to be this term cathodic, whereas the glucose sensor could be anodic. And then we also make a lactate sensor. And whether we make a sort of generation 1 lactate sensor or generation 2 lactate sensor, it can be what's called anodic or cathodic. So amperometry is often something that we use with these enzyme-based electrodes. We also describe voltammetry. We describe what's called a redox probe and a pH probe, and we describe ion selective electrodes. And I should have said the word potentiometry here. We describe voltammetry, and voltammetry is cyclic voltammetry. Voltammetry is not used much in actual products, but we do use voltammetry a lot during the preparation of sensors, almost like a quality control technique. but we do describe that we do use voltammetry in some of our products. For example, there's a molecule out there called capsaicin, and we describe how we use voltammetry to measure capsaicin, and we do a demonstration on that. So voltammetry is kind of electrochemistry's version of optical spectroscopy. It's harder to generalize when to use voltammetry. Amperometry, I can generalize on it. We generally use it with enzyme-based systems, especially ones that have a cofactor, which is oxygen, which gives you hydrogen peroxide, or the cofactor is NAD+, which gives you NADH. So it's easier for me to generalize with amperometry. Voltammetry is not so easy for me to generalize. And it's very hard for me to give commercial applications or examples of its commercial use, apart from stuff that we do. And I started going on about pH, ion selective electrodes, and I really should have said potentiometry. We do discuss potentiometry, and we do demonstrations on potentiometry as well. And then impedance spectroscopy. This is becoming, I think, really important now, impedance spectroscopy. If you're trying to make what we call binding assays, a binding assay is, I've taken a electrode, I've put an antibody on there, I've put an aptamer on there, I've put a receptor on there. So I've put some specificity on that surface, and then it binds to my target. Because you're binding to the surface, you're changing the electrical properties of the surface. And impedance spectroscopy is a pretty good technique when thinking about binding assays. I can generalize more with that. If we're doing a binding assay, then we use impedance spectroscopy. If it's an ion selective electrode, then we generally use potentiometry. If it's an enzyme-based electrode for small molecules like glucose, lactate, then we tend to use amperometry. And voltammetry, we do use it. I don't think it's used so much in commercial applications, but with the new chipsets, it actually is possible. Before it was troublesome for electrical and electronic engineers to make circuits for voltammetry, but that's really got a lot easier these days. I will talk about this at the end, but we're actually making we call it switchable single-purpose circuits. So what I mean by switchable single-purpose circuits is, if you're trying to make an alcohol sensor, for example, we'll sell these by the reel these days, and we'll just flash them to, for example, run a glucose sensor, or run an alcohol sensor, run a nitric oxide sensor, run a pH sensor. So I think the days of analog electronics are kind of, at least in the world of biosensing, are reducing, and it's really becoming a coding exercise now. There's less value in designing. If you want to design ASICs, that's one thing, but designing analog electronics using discrete components, I think those days are over. And I'm hearing engineers saying to me, yeah, this is becoming a programming effort. It's not becoming a sort of analog design effort anymore. So it is hard to, we do have a lot of material about what techniques to use with what biosensors. We have the workshops. That's probably the best place because you can ask the questions directly. We do have at least 3 places, the academy, the application zone, and also the educational zone video. And also I've just added some comments here as well. As a side note, yes, we are, like, for example, if somebody now has a glucose sensor, then there's a glucose circuit, and you can sort of switch the circuit from being glucose or lactate, etc., through Julie. Just a comment, if you are getting into electrochemistry, then, this is the old-fashioned way of doing things, and really electronics and the R&D equipment has just got a lot smaller these days. So don't be having behemoth-type potentiostats. Make sure that you keep them small, because it's just, what am I saying? By keeping it small, you're kind of keeping it closer to what a final product would actually look like. So for example, we have, this is an Abbott Freestyle, so I'm not going to suggest that's ours. It's not. But I'm just saying, the kind of electronics that are in there, these are much more, at least through Zimmer and Peacock, readily available these days, these kind of small circuits. So this is a tough question. I'm looking to monitor glucose, lactate, and nitric oxide in cell culture. The following slides, Aftab was just saying for characterization, so I'm just watching the chat as well. cycle voltammetry is something we often use for characterization. It's true. Like when we're doing biosensor building, the cycle voltammetry is something we use for characterization. I'm just gonna So the question here is doing cell culture. They want to measure glucose, lactate, and nitric oxide in cell culture. This is also something that we're quite interested in as well. I mean, this is an image. This is a picture I took a while back, and we were kind of, because obviously when I look at that, it's elegant in some ways, but it's dumb in some other ways. That people want to control the environment in these situations, but they'd at least like to know what the environment is like. So this is the slide I made, and sort of said, I at least want to be able to detect glucose, oxygen, and pH in a system like this. So what we have at ZP is, we obviously have biosensors. We have pH, we have oxygen, we have lactate, we have glucose, we have nitric oxide, for example. I say it here, the word wrong is a little strong, but it's the wrong form factor. It needs to be, there's a gap between the sensing element will work perfectly well in a cell culture. It will detect those things, but it's how do you bring that sample to the sensor? So the sensor really has to come into the cell culture. So there's an engineering gap. Again, I mentioned Industry 4.0 earlier on. I have people seen, definitely, I was in ACMA, which is a big process conference in Germany. And in ACMA, people were talking about Lab 4.0. And Lab 4.0 is the same thing, that sensing electronics to cloud. And then actually, if you follow the OPCUA, Open Platform Communication United Architecture, then other vendors or other equipment should be able to call upon your data. And that's definitely what we're trying to do at Zimmer & Peacock. So I can describe the workflow, but what I can't describe is that piece of engineering that makes these sensors actually go into those reactors. So you take a sensor like this, you want to place it in here. We could do that, 3D print some rods, do some soldering, so that can happen. It's not beyond the wit of man. It's just we haven't done it. So if we were saying a glucose sensor, take the glucose sensor. It has to go essentially for me, through the lid at the moment. I understand this. With bioreactors, you have unusual things like sterility, in-place sterilization. It's not an easy application. So we do have the sensors. We probably have the electronics as well. And we definitely have the app capability, or at least the connectivity to the cloud capability, and we could send the raw data to the cloud. So the easiest one for me would be, can we measure pH in a cell culture? I would almost make it, the two easiest things to do are probably, can we measure pH and can we measure glucose? The reason I mention that is because pH is fairly simple sensor and fairly robust. The glucose sensor for us has had a lot of investment, so it's pretty robust. Lactate is a weak enzyme, and I think the run times that we've kind of got so far are like 8 hours. We just can't, we have to put the investment in. So I'm not suggesting lactate sensor. And the nitric oxide sensor, we just haven't had as much development time on the nitric oxide sensor. We've used it in a discrete manner, but not continuous manner. So if somebody was asking me, I want to instrumentize a cell culture, my honest would say start with pH and glucose, at least if you're starting on the ZP platform. So you have your glucose sensor. There is some engineering in order to put it into that cell culture environment. You need the electronics. Those can sort of come from companies like Zimmer & Peacock. You need for us, we would if we were doing a product development around this, we would be sending our data immediately to the cloud. We have something called Julie, by the way. I haven't at all mentioned Julie. DJULI. Julie is a cloud system from Zimmer & Peacock that can receive electrochemical data. It can process it, and people can call upon that data using an API, an application programming interface. So we can send the data to the cloud, at which point then we can actually put it through filters and templates and turn it into concentration. So it's not, what's in place at the moment is the sensors are in place, the electronics are in place, the connectivity to the cloud in place, the cloud's in place, the ability to turn raw data into concentrations in place, but actually making it work robustly in that application with us is not in place. And again, people can call upon it using API. I do have concerns, and I have to put them out there straight away. Concerns would be drift, pH sensors, they drift. The fact that you're putting the data into the cloud could potentially mean that you can compensate for the drift, but as long as, of course, the drift is consistent. And it means gathering hundreds of, I say data points, but experiments in order to kind of characterize that drift. Loss of activity, I've mentioned lactate, I'd be concerned, especially for lactate, I'd be concerned about loss of activity. And then my other concern is just details. There's lots of details like, sterilization, would be a detail. What does that user interface really look like? So there's, loads of, I can make it, or not make it, but, it can sound quite elegant, but actually, it's always the devil is always in the details. So I don't want to ignore that. All right. Question number 4 is around about alcohol sensors. So I'll go a bit quick. The question really is, we do have an alcohol sensor, but when we do have additional materials on that alcohol sensor, so that alcohol sensor is not some plain electrode. The alcohol sensor is specific because we've put an enzyme on it. So this is a shorter answer, but yes, it's been made specific. You can use this alcohol sensor either by we drop samples onto the sensor, or you can have the sensor in the reactor itself. The questioner was asking whether we could do alcohol detection in urine. The quick answer is urine's it's probably a good matrix for us because it's a it's a slightly ionic liquid, which is good for electrochemists. We do have again that stack of technologies where if somebody has a urine sensor and they have one of our Sense It All platform, for example, we can send that data to the cloud. And this is important because if you're going to test alcohol in urine, you can test that on pre-existing equipment, which is important because you can test it on pre-existing equipment and test it on the sensor from Zimmer Peacock, and then work out the calibration factor. Because sensitivity, so there's two main parts of the equation. There will be sensitivity and offset, and sensitivity and offset are probably matrix dependent. So even if you get an alcohol sensor from us, have we tested it in urine? No, we haven't. Will it work in urine? Yeah, it'll work in urine because urine is just essentially water with some salts in it. It might have some urea in it, but the enzyme should allow you to effectively pull out the pull out the alcohol sensor. So we can, if you want to calibrate this kind of system, then the alcohol sensors from ZP will work. The Sense It All platform ZP should work. But then you'll have to do some work with us in understanding. Probably best to have a third-party way of measuring that alcohol in that urine so that we can come up with a calibration curve from that. Question number 5. So we do get this question quite a lot is, if you're using like ZP sensors, whether it's potassium, pH, oxygen. I mean, potassium's useful, is one we haven't touched upon today, but if you're using one of these sensors or sensing platform from Zimmer Peacock, whether it's potassium, pH, oxygen, lactate, glucose, alcohol, nitric oxide, hydroperoxide, ammonium, these are things we mentioned today. We have the capability of taking this little board and just making it, for example, potassium sensor specific. And that would be basically put into potentiometric mode. So we can then sell these things on the reel. So you can have a whole reel, let's say 10,000, or 10,000 is a large number, but you can have people are ordering it like this, they order 10,000 of these little boards and they've all been flashed for potassium, or they've all been flashed for pH, or they've all been flashed for oxygen. So the reason I say this is because there's a lot of effort going into the design of analog front end and the design of digital back end, but actually this stuff is becoming quite commoditized now. And so this one little circuit, we make it a sort of OEM product, so original equipment manufacturers can get it, and we just flash on it, whether it's going to be used for a potassium sensor, a pH sensor, a glucose sensor, a nitric oxide sensor, etc. Right, so the time is 8:30. Spoken an awful lot this morning, so I shall. And as I say, you can also then view that data also in Julia as well. And this is what it looks like. It's a fairly small board. It's perfect for things like wearable sensors, but also just in general, you know, because of the size of it, we can make the manufacturing density become quite high, which means you can drive down the costs. So question number 1, detection of ammonia and hydroperoxide. I suspect that we have these sensors, but we don't give out 4 to 20 milliamps. We're not CAN, we're UPC-UA compatible. Techniques to use for which sensors: amperometry for glucose for enzyme sensors, potentiometry for ion selective electrodes, impedance spectroscopy for binding assays, and voltammetry for characterization during manufacturing. And we also do use it in our products. One of the best places to find out about that is really at those workshops. If I was working on a sensing system for cell culture, I'd actually be starting off with things like glucose and pH. Lactate, I think, at least from Zimmer and Peacock, you know, you'd be very disappointed with an 8-hour runtime. You know, we're working on it, and lactate and 8 hours works for sports applications, but it is tough. Alcohol sensors, the alcohol sensor exists. It's got an enzyme, so it's specific, and you can also just get small little electronic boards from Zimmer and Peacock as well, and that was the switchable single-purpose sensor circuit. So I will wrap up now. Say thank you very much. Thank you to AFTAB. Congratulations on your personal good news recently, AFTAB. Really delighted, and I will be speaking to you later on. All right, so take care, everyone, and thank you. All right, take care. Bye-bye.